So good evening, everybody. So today I'll talk about Linux container technologies, but because I had no idea who will be my listeners, so I have some scary material and some lightweight. So, but before I start, I'd like to ask a couple of questions to you. So first of all, raise your hand if you know what is Docker. Okay, good. Raise your hand if you know, if you use Docker every day. Less. Okay. So raise your hand if you know what kind of technologies behind. Okay. Okay. The same. Okay. So let's try to start. Before we start, I will say that all stuff I will talk about will be in context of Linux, because some words like container could be interpreted like different way depending of context. So I'll give some examples in C, but it's not like mandatory to know C. Just if you are familiar with IT technologies, you probably know some languages and you can like easily understand what is happening there. But anyway, if you don't understand something, please interrupt me and I'll explain. So in some cases, if you are interested to like understand or get some extra knowledge, I'm providing links to the online Linux kernel source browser. So you can use my slides, click to this link and go there and figure out what is around, what is like code really look like. So, and I use kernel 6.2. So because when I updating my slides, so I had this presentation before, like a couple of years ago. So, and I figured it out today and yesterday, I figured out that many things are changed in kernel. So this is why I kind of fix the version. So, but okay, everybody is using Docker, but one more question from my side. Who is using Docker Compose? The same people, okay, good. Let's check. What is happening here? This is two files. It's a question to people who like familiar with Docker Compose something. In 2 words.
The left file is configuration for container. So here we initializing some base image from Python 3 level. Afterwards, we move into working directory, we executing some preparation stuff and so on and so on. And on the right side, there are 2 containers. The first one is probably main application, server application. Mm-hmm. We initialized on some port, and the second one, I guess it is database for the mm-hmm. application where they place some sources for that application, something like that.
Excellent. But if for people who is not familiar with Docker technologies and who like not regularly use it in his life, so what is happening here? I will draw a small picture. So we have 2 descriptions. First, for some file system snapshot, for some image, it's here on the left side. Second, this is description of couple of containers, as you say. But what is happening? So you run some code in your Linux machine. actually you have to write something like docker compose up. From some place, image or snapshot of file system is being downloaded here. So this is like this name of image. So it's like some particular snapshot of file system which contains some Linux stuff and Python 3.11. So we have like image file system here. Second, on this Python 3.11 image, we make some extra steps. We add something to file system, some extra packages, right? It looks like we run the same command in the Linux, right, in the Linux shell, but it has been applied to this image. And after these steps, we have like better configured image for some application. Doesn't matter, but it does. So Docker Compose. We use Docker Compose to create some virtual environment where we have running some set of processes from this image. No, not this, sorry, from this image. This is like Python 3 something. And we have second virtual environment, which the same way we are downloading from some repository. It has a name like Mongo. Just run here. So what's the story behind this quite simple set of commands creates full illusion of the server, right? Inside a computer, inside of Linux machine. So we like have virtual machine or container here, which is, if we go inside this container, we will see that this is like very small, like Linux machine with some file system, with some processes running inside, and this. But not only this. Also, here we have a network, right? And if you have a look here, you will see that this container has own network IP address, right? And this container also. And those containers can talk each other. Where it happening? It is happening here, not in this network, right? Not on the host machine, in some environment, right? And today I will try to explain how does it work, what kind of technologies behind in Linux kernel we have to implement such behavior. So actually, when we say Linux container or Linux virtualization technologies or Docker or I don't know, something based on Docker, we usually use only two interfaces, only two like things. It's namespaces, which we have from for years we have namespaces in the Linux, and control groups. We also have control groups in Linux for the 10 or 15 years. So, but what is Docker? Docker is just set of tools actually user space tools, which exploits such technologies. So namespaces, this is isolation technique. Like here, I need to isolate these processes from the host, right? I need to isolate those processes from the host and from this process group, right? I have to isolate network. I have to isolate, for instance, set of CPUs. Why? Because I have to have predicted behavior for some processes which I run on my host machine. I have to keep control on my host machine, right? Okay, second technology is the control groups. So it's like set of features of the Linux kernel which can control this kind of resources. So, and during our conversation, I will try to answer the question how they do this. First of all, I have to remind you how processes looks like in Linux kernel, in Linux. So if we usually in IT world, people say process, thread, and so on. But on the different operating systems, implementation are also different. So if we have a look at Linux, we will see that this is like multi-thread application, or this or this. This is like main thread. This is like child thread or something. So if we have a look at the properties, we have special attribute PID, process ID, well known, right? And thread group ID. So, and if you see, the main process has the same value in PID and thread group ID, but other have different process ID, but the same group ID, right? This is like, it looks like we run many copy of this application, this process, and just set the same thread group ID to inform Linux or kernel or user that this is like multi-thread application. But this is not enough, because when you have multi-thread application, usually this application share at least memory, right? So interesting. Let's move on. So if we go to some handbook and have a look at the chapter or section which is explain how to create processes in the Linux, you will see something like this, right? So they say, okay, everything is just a copy of the parent, and interface is like this. So when parent copy or create a child, so child has new process ID, fork return 0, it means you are a child, just run some, I don't know, child code, child source, right? Like this. That's it. And they are working like this. But if we have the implementation, we will see that this is actually a fork system call. But there is no fork. There is kernel clone. Why it's interesting for us? Because from the initial stage of the Linux, some years ago fork was a fork. Trust me. But now fork is a clone. So, and clone is one of the interfaces for creating namespaces. In this case, it just create or use process ID namespace. So if we go more deep to the Linux source code, we will see the following. So this is task struct. Task struct is a structure which contain information about some process or thread. For us, it doesn't matter, right? So, and we see here PID, we see here thread group ID, right? And also, we see here NS proxy. NS proxy is a pointer to the NS proxy structure, which contains information or pointers to the namespaces. This is PID namespace, which is usually, if you don't run any container, shared between like all processes you have, right? So, but if you start running containers, you will see that it's different. So, and so on. Okay. What kind of interface we have for namespaces? It's only three system calls. Clone, we already know, right? It just, if we have some process, we make a copy, make a clone actually, and automatically all resources are shared between creating process and process which is created, right? Second, unshare. This is like, if I don't like to share the resource given by parent process, I will create my own namespace and put this resource there. Okay, for the process ID, what kind of resources we share or unshare? It's just sequence of numbers, right? Like unique numbers of process IDs. So, and also we have set NS, means set namespace, is about to put or start sharing some kind of resources with other resource group. If you create okay if you create, for instance, if you create multi-thread application, you have to share memory, right?
As I know, fork doesn't share memory.
A fork doesn't work at all. Clone is working, right? I will show how clone works. You remember, right? This is fork. There is no sharing, no unsharing, nothing, right? Okay. A couple words about procfs. Probably not everybody familiar with it. So in Linux kernel, there is some special driver, special file system, which provides kind of file access to the processes. So when why I'm talking about this, because we can like have a look or inspect any process just looking at some files in the procfs. So for instance, this is my like try to understand what kind of namespaces I have for the current process. I just go to the procfs, list ns, and I have set of objects. So I can go deeply, I can inspect each namespace, and yeah, that's it. So, and I will use this file system in future examples. Clone, especially for you. So look, this is clone. This is signature for clone. The key part of clone related to our topic, this is flex. This flex the same for fork, for clone, sorry, and for unshare, right? And this is possible options. Calling the clone, I can control what I will share, just passing this flex, right? So, and actually you can kind of create your own monster from set of sharing resources between set of processes, right? Okay. So, again, this is like mount namespace. This is view for file system 3, right? New UTS, Unix Timesharing System. I will tell about each of them. IPC, PID, and user. Like making a clone of the process, you have to create your own, you can create your own file system, UTS, and so on. Or you can share everything with parent, right? So this is example for mount namespace. Very clear, right? Just unshare. It means like I am a parent process, right? I'm a process. So I don't like to share mount namespace with my parent for some reason. I just unshare. And it means automatically that I create the new file system namespace. And I can make some changes there, and parent won't be informed. Yeah, this is how to use it, right? So, and actually we have like special system call for working with mount namespaces. This is signature, but if you want to test it in command line, in bash, you can use like mount utility, which does the same actually. Then you can have here. So it's quite interesting that you can define how each mount point will be visible or invisible for other mount points. So this is, yeah, you can make your mount point shared or unshared. You can like follow the rule or policies for mount points from your parent or parent processes. You can make mount private. It means only in your, if you mount something, only your group of processes will be able to see this subtree of file system, right? Or even you can make it unbindable. You mount and nobody can unmount it if you don't allow. And also we have like R, like rbind or something. It means that for file system where we have many mount points, we can recursively like remount them. This is a couple of examples. So imagine we have this file system at the beginning. This is like initial state. So if you mount like def to mnt, we will like move def to here, right? You see this. We kind of shadow underline file system. So if you use make shared, you will see that it's like copied, right? So you share mounting point. So, and if you bind even inside, you will see the same, right? This is available from the command line. You can play with it. So, Unix Timesharing System. This is like very unsigned name because when computers were big, people are sharing time to access to these computers, right? This is about such kind of sharing, not about sharing time, but about sharing machine time, right? And actually it's about, because when people start reading this, they like confused why Unix Timesharing System share information about host name, right? It's strange. But anyway, this is UTS namespace. So it's actually describe only name, which we have here. You know this, right? So this is like container I created by Docker, and I said I would like to have host name, this my container host, and when I enter to this container, I see this. Why? Because doing this, I create a new namespace and new name for host, right? Yes, this is, I won't go deep inside this, but this is like creating some thread with new UTS namespace, and if I use set host name, it will be applied only for this child process. PID namespace, or process ID isolation. So when we create container, we create new PID namespace. So, and this is like different PIDs in different namespaces. So imagine this is a host. So I have usually first process ID, so I can create several of them. And when I create new process ID, process namespace, process ID namespace, I have again one. But in this process ID, process PID namespace, it has number 1, but it's still here. And we have the same access to this process, but via different numbers, via different IDs. But all of them have a like meta parent, which is 0. So we can check it. So it's just a reminder. Usually we have like meta parent. This is parent process ID, right? And if we try to figure out what is parent process ID for init, for the first process, we will see that this is 0. So, and if we run something in the container, we will have different view. This is top, right? So in my host machine, I'm for people who is not familiar with this, this is what it does. It getting image with this name, it's like here, and create the container based on this image and run bash inside. So if I do this, I will have a bash running like in my process 3, no problem. But if I go inside the container, I will see this process 3. Only two processes, right? That's it. And again, this bash has a number 1, and has a parent number 0. But here, it has a number like too long to read, and there is no 0. 0 somewhere above. Okay, IPC namespace. IPC namespace related to some IPC resources. IPC means inter-process communication. So we can easily create like new namespace by using unshare. And for instance, we can create message queue. And this message queue will be shared only with processes which I create from this particular process. So it means that future you will see that we can control resources for some namespaces, but this is like a way to create this group of resources. Okay. User namespace. User namespace is related to user ID and username. So if I am kind of user, I can run something like who am I? I will see my user ID, my group ID, my name, and so on, right? But what if I want to have the same user and the same user ID and group ID in the container? Usually like www data or something, I have to like access via some particular user. So, okay, the user namespace provides us the same functionality. Have a look at this code. This is just, you know, the same unshare, right? It prints user ID, group ID, and username. This is here. And after unsharing, I do the same. But I see that user ID something strange and I am nobody. I can create users by using System API, like add user or something. It's the same. I can set password, I can set user ID, I can set group ID, and I will have the same user with kind of the same IDs, right? So, and quite interesting, but I have no time to explain it deeply. Network ID, network namespace. If you have regular Linux machine, right, you can type something like IP addresses or IP interfaces or something. You will see very long list of interfaces, address spaces, and so on. What if I want to have like different, the same IP addresses, in different containers? Or if I want to have different routing tables for the same addresses, right? Or even network stacks. So it can be given us by network namespaces. So you can play with this IP utility. It's regular IP management interface, command line management interface. So what it does, it creates new network namespace. It like executes IP inside this network namespace, new network namespace. It's kind of default management interface, right? If I go to the Linux machine, I like type IP and I see everything. But if I created some separated network namespace, I have to run IP inside this namespace, right? And this is a way how to do this. So this is like list links, physical links. This is delete the same namespace. This is kind of setting local interface, upping it up. And yes, we can even ping this and so on. Ping, bind, and everything we usually do with IP addresses. So if we make some small program, it looks again like regular unshare. And here, running IP config, we see only one, which is created there. We cannot see host stuff, right? Control groups. Before I go to the control groups, probably you have some questions about namespace. No? Okay. Oops. I'll skip history. So, yeah. Control groups and subsystems. So in Linux, in this particular topic, the subsystem is a module that provides some set of capabilities for managing some kind of resources. I will tell a bit more later. And control group, it's kind of interface, but to think simply about this, you can just think that this is set of parameters associated with some type of resource. For instance, CPU, okay, or memory, okay. How it looks like in the system usually. Imagine this is like resources of some server, of some hardware machine. You have some set of processes, and process usually has some resources, some RAM, CPU, devices, I/O objects, and so on, right? And you have many processes. But also you have set of devices. I'm talking about like physical devices, but it also can be some virtual devices. Just from the Linux perspective, it's just a set of files in dev file system which provides some access, like read, write, or something. So you have some set of cores, CPU cores, right? So it's again hardware resources, right? And you have again RAM. It's also, I'm talking about hardware, about physical RAM, but it also can be applied to the virtual, not virtual, to the swapping space, right? Not virtual addresses. Each process can have like own virtual address space. Imagine that you want to kind of classify how to use all of these resources without thinking about how many resources should be provided to each particular process, right? It's too complicated. So, and control groups is a way how to do this without thinking about each process. For each subsystem, we can have a controller. We have controller. So there is a set of controllers. CPU controls CPU time, memory controls memory, block I/O controls access to the block devices, because it's not so easy when you have many high-loaded processes and limited set of block devices. So CPU set controls kind of affinity of process cores to some processes. Devices, it's device files actually. Freezer, very nice, I'll tell about it. PIDs, this is number of processes which can be created inside of process group. networking, and some priorities. This is actually more than for controlling and monitoring network flows. So cgroups also are available via some file system. So cgroups file system looks like you can start from this. So I am on the Linux machine, right? I can cut something for, this is like, it's my current process ID. I forgot to like replace it by $2. So cut something, and you will see very nice picture that I am in some control group which has name user slice user 1001 slice blah blah blah. Okay, let's see what is it. This is file system relates to this particular user and this particular process. So, and each of these files, it's actually a file in file system, but this is file interface to the control group. I can read file to get some parameters. I can write file to set some parameters if it's allowed. And also we have similar set of files for the highest point in hierarchy. Okay. There is a set of commands when which can I use to create groups. For instance, create this is I am creating the group which includes memory, CPU, controllers, and I mount this group to some point in file system, right? То есть, to create control group, I have to know which controllers will be in this group. For instance, here I'd like to control CPU and memory. I can specify more, and I have to have interface how to control this group, right? This is why I have to mount this somewhere, right? I will have the same set of files, which is we already saw there. Yeah. Okay. So I can delete the group, obvious, right? There is no point discuss it. I can classify the process. I can pick the process and put it to the group, right? And it looks like here. This is like, I'd like to classify this set of processes to this group. You remember, I created it and mounted to this place. So, and in each group, I have special file tasks. If I cut it, I will see that set of processes, but if I like write to this file, I will put process to this group. So if at this moment this process belongs to some another group, it will be removed and moved to new one. I can also run something in the group. Just not create process and move. Just create and run in some group. For instance, I don't like that Google Chrome eats my memory. I create memory group with some limits and run from there. Okay. This is interface for getting parameters. So also you can, in some cases, you can write to the control group just echo something, as you saw before, but this is proper way to use it. Sorry, this is for reading parameters. Yes, it's cut. In many cases works. This is for writing parameters. The same. for instance, here I'd like to specify that only 8 cores will be shared recursively in this group. CPU set, very nice. I have set of cores, and I would like to keep like 2 of them, for instance, for like system critical something. I don't provide this cores to any process except this critical something, right? Okay, this is just overview. So this is CPU. It's about CPU tacts, right? This is a set of parameters for scheduler. I can tune schedule procedure for scheduling this group. I can set like CPU quota. I can set CPU like ratio with other parts, and I can have some stats here. So CPU accounting is about like just counting. It's very nice to use. Usually many tools use this, even if they use like something via different interfaces, but it's like it's collected all data from the process tree. This is devices control. It's like whitelist, blacklist. If you put some device to the blacklist for the group, for instance, you don't like that your like archive manager will use, I don't know, sound card. It's easy to do. Freezer, very nice. Imagine that you have kind of I don't know, production system which serves customers, and at some point some like random, not random, cron controllable process like archiving or something happened, and this is like end of month and so on. Everybody crazy about like finishing their work. You can just get some set of processes and put to freeze. And what does it mean? They just will be stopped in the condition they are at the moment. And after you finish something, you can just put them back. And it looks like time machine, not time machine, but like stops the time, right? For some set of processes. Very nice. I like this. Memory, it's not all parameters. Okay, you can read it in the docs, but we can obviously set limit of bytes, soft limit for memory scheduling. We can provide some information for out of memory killer, and yes, it's about this. IO operations. IO operations, it's quite interesting when you want to kind of reserve some set of buffers, network buffers, or some set of I don't know, yeah, maybe bandwidth of some operations or for some devices. It could be controllable by this memory. So if you have some question, you can ask now. You can write me email. I do not promise that I answer each email, but I will try. And please scan this and answer 3 or 5 questions about what do you like or dislike or something. Thank you for listening.